Hello, we are going to present our topic NMix Q-learning, investigating overestimation bias of Q-values. The overestimation bias of Q-values refers to a situation in which the estimated value of an action is higher than its true value. For example, let's consider the case of rolling a dice. The expected return of rolling a fair dice is 3.5. However, if you take the maximum value over all the outcomes from the multiple rolls, the estimated value is very likely to be 6. If overestimation does not occur uniformly across all states, it can lead to a suboptimal policy. DDQN is known to mitigate this issue by performing the max operation inside an additional Q network. And averaged Q-learning and max-min Q-learning both utilize multiple Q networks. In particular, max-min Q-learning takes the minimum operation over multiple Q networks for each action and then selects the maximum value among them. Then we can naturally ask the question of how effectively the mentioned Q selection strategies can alleviate the issue of overestimation. And we devised a new strategy NMix, starting from the question, how about taking min operation along max Q values of each network, which is intuitively the reverse direction of max-min. Our approach is quite intuitive. By initially applying the max operation over the action space for each Q network, the resulting values are valid within the context of DQN. To mitigate overestimation, we then find the minimum value among these maximum values. This process can be seen as constructing a milder Q target, effectively preventing the detrimental effects of overestimated Q values. Comparing NMix and max-min, we have mathematically proven that the outcome of NMix is always greater than or equal to that of max-min. In short, the maximum values of each column will always be the same as or greater than the minimum Q value of each row. However, please do not misunderstand that NMix cannot alleviate the overestimation problem. When compared to DQN, NMix naturally handles overestimation by utilizing the min operation in contrast to DQN.
Following the proof of the previous slide, we hypothesize that NMix will overestimate compared to max-min and DDQN, but will still be able to mitigate than DQN. We established two experiment objectives. We want to observe the impact of Q-value overestimation bias across various environments. To achieve this, we measure the average return over the 3 Atari games and also estimate the mean of estimated Q value for each time step during training. We also examine the robustness of the algorithms in simplified stochastic MDP environment. The average return over 3 Atari games is as follows. NMix performs well compared to DQN, DDQN, and averaged Q-learning, and performs similarly to max-min Q-learning. We also designed the experiment of measuring mean of estimated Q values. For each step during training, we sample a batch of state action pairs from the buffer. Then compute Q values from each QNet in NMix for all the state action pairs in the batch. We measure the average of these Q values. NMix estimates Q values lower than DQN, DDQN, and averaged Q-learning, which corresponds to the performance evaluation in the previous experiment.
Also, to investigate the algorithms in stochastic environment, we composed a simple MDP environment. The MDP consisted of episode length 1 and 2 actions, left and right. When agents choose the left action, they receive one of 8 randomly assigned rewards, and mean of those will be the mu. When mu is higher than 0, the optimal policy will likely to select the left action, and overestimation will make the Q value larger, helps agent to go left. On the other hand, for negative mu values, underestimation will be helpful. The metric we focused was the distance to the optimal epsilon greedy policy. In this experimental setting, epsilon value was selected as 0.1, and the probability of choosing optimal policy was calculated as 0.95 as follows. These are the results of our MDP experiment. D is the distance between agent policy and the optimal policy. When mu is positive, distance is decreased, and vice versa. And let's take a look at its situation. When mu was positive, we can observe DQN, the light green line, has lower distance compared to DDQN, the green one. This means that overestimation is affected in beneficial. However, when mu was negative, we couldn't find a clear tendency. To wrap up our project, we devised NMix Q-learning which alter the direction of processing Q values among N networks and hypothesis it logically, and observed the impact of Q value overestimation bias across various algorithms and environments. NMix was very effective in decreasing the overestimation bias, and as hypothesized, the amount of overestimation was larger than in max-min Q-learning, and following inequalities were satisfied. However, in simple NDP environment, we were not able to discover the behavior tendency of Q-learning algorithms, especially in the case where underestimation is beneficial. We will take an approach to deal with them later. Second, we are looking forward to evaluating more complicated environments that are related to overestimation and underestimation benefits. Additionally, more concise mathematical convergence proof and the additional ablation studies will be really helpful in discovering the nature of NMix Q-learning. Here are the references, and thank you for listening.